Welcome back everyone, and in this video we will try to discuss a few examples related to the application of universal law of gravitation, or how to use this universal law of gravitation in a few examples. So I will be explaining a few examples in this particular video, and I will try to continue these examples in the further upcoming videos also. Okay, the first one we'll be doing is that let's say the first example where we can apply this is, let's say we have three masses. So for the sake of simplicity, I will consider three equal masses m, m and n. So I have taken three equal masses, each being equal to m, and which are at the corners of an equilateral triangle. Let's say they are at the corners of an equilateral triangle of side A. So the side length of this equilateral triangle is A. Now we need to find in this situation the gravitational force acting on one mass due to the other two masses. So if I take any one of these masses, this mass m will be experiencing a force due to this m present at this corner in this direction, and as well as this will also experience a force due to this mass m in this direction. So similarly, even if you take these two masses, if I take this mass, this experiences a force due to this mass and as well as due to this mass in this direction. So each mass in this particular situation experiences force due to the remaining two masses. Now what we need to find in this situation is, we need to find the resultant of the, if I take this mass, we need to find the resultant of gravitational force acting on this mass due to these two masses. So that's what we are intending to find in this situation. Okay, since it is an equilateral triangle, this angle will be equal to 60 degrees, because if we join the position of these three masses, these lines, the angle between these two sides will be 60 degrees, because it is an equilateral triangle, and in an equilateral triangle all the angles are equal and as well as all the sides are equal. Okay, now if we take this mass, it exerts a force on this mass in this direction, and the magnitude of that force is given by G into m, the product of masses, by a square, where a is the separation between them. Okay, this is the magnitude of force exerted by this mass and on this mass. So for the sake of simplicity, we will just give these masses some numbers. Let's call this mass number 1, mass number 2, mass number 3. Remain that these numbers are just for the sake of identifying different forces. They do not mean that they have different masses. All of them have the same mass. Okay, now let's represent this as force acting on 2 due to 3. Force on 2 due to 3, which is equal to Gm into m by a square. I'm just representing the magnitude in this situation, and the direction of that force will be in this direction. Force on the second mass due to the third one will be in the right direction, and the magnitude is G m square by a square. So this is the force acting on the second mass due to the third mass. Similarly, the first mass will also exert a gravitational force on this second mass, and that is given by the same again from the law of gravitation, G into the product of the masses into the separation between them. So the magnitude of the force also comes out to be the same in this case, but the difference is that the direction will be different. It will be along this line connecting these two masses. Okay, so now these are the two different directions in which these two forces act. Though the magnitudes of the forces are same in this situation, but the difference is they are acting in the different directions. Remember that the forces are vector quantities. So if we want to find the total force acting on this, total gravitational force acting on this mass, it is nothing but the vector sum of these two forces, the vector sum of these two forces. So since we know the magnitudes of two forces and as well as the angle between them, so we can find the resultant force acting on this mass by using the parallelogram law of vectors, where in parallelogram law of vectors we can find by using parallelogram law of vectors we can find the magnitude of resultant of these two vectors. Okay, let's assume the magnitude of resultant as F2. Then from the from the parallelogram law of vectors, we can write this as F21 square plus F23 square plus 2 product of these two forces into cos of angle between them, and substitute these things, and you will be getting the resultant. You will be getting the resultant force acting on this second mass. You will get the magnitude of the resultant of these two forces acting on second mass, and the direction of this force will be it can be found from the parallelogram law of vectors itself, where we derive a formula of something called alpha, where alpha is the angle made by resultant with one of the vectors. Or in this situation, observe that these two forces have equal magnitudes, so the resultant will be in between these two directions and it will make an equal angle with the two forces, because these two forces have equal magnitudes. So whenever you combine two vectors of equal magnitudes, the resultant of those two vectors will make equal angle with both the vectors. That means the resultant will be in this direction, F2, and it makes an angle of 30 degrees with this direction, and as well as 30 degrees with this direction. Okay, this is the one way of finding the magnitude of the resultant force acting on one of the masses and the direction of the resultant force. See that you can apply the same thing for the other two masses also. So there is another method by which we can find the resultant force. I hope so you can continue the calculation from here. I am not doing it. Okay, now let's proceed to the other way of finding the resultant of the forces. Hope I will erase this part. And I will try to draw this diagram once again. So the masses are the corners, three corners of this equilateral triangle of side A each. Now we'll try to find the resultant force on this. The magnitudes of forces will be the same in all the cases. Let's call this 1, 2, 3. You can represent these numbers whatever you want, whatever the way you want. I'm just giving the number something like this. Even if you don't represent the numbers, it's not going to be a big problem. If you are a starter, then the numbering will help you to avoid confusion. And in this situation, these are the forces. Suppose if I pick this mass, the force acting on this mass due to this mass will be in this direction, and magnitude will be gm square by a square. Let's call this F. Okay, F. Similarly, the same magnitude F will be exerted by this mass on this mass, but in this direction F. Now what we can do in this situation to find the resultant is, we can just use the vector form of doing things. Okay, the vector form. So what we can do is, I'll pick an axis such a way that something like this. I will pick my xy coordinate system something like this. The y-axis is the angular bisector of this, and x-axis is perpendicular to it. So if y-axis bisects this angle, it makes an equal angle of 30 degrees with this direction and 30 degrees with this direction. So the forces will look something like this. Okay, I'll just represent the forces here itself. This is 30 and this is also, I'll just extend them. This is also 30 degrees. So each force F is making an angle of 30 degrees with the negative x-axis. Now in order to find the resultant force, what we can do is, we can find the vector component of these two forces along x-axis, along x-axis and y-axis, represent them in the vector form and add both of those forces. First we'll try to represent this force. So this force F is making an angle of 30 degrees with the negative y. So we can resolve this into two components, F cos 30 and F sin 30 along negative x direction. Similarly, this force F acting in this direction can also be resolved into two components. F, it's making an angle of 30 degrees with the negative y-axis, so it can also be resolved into two components, F cos 30 and F sin 30. F cos 30 and F sin 30. So we can represent them in vector form, something like this. So this force, I will represent that as this one. The first one, let's call this force as the first one. So that can be represented as minus F sin 30 I cap minus F cos 30 j cap. This force, this one. And similarly this one. So this force can be represented something like this. Let me call it the F1, something like that. Okay. And the second force, let's call this F2, the second force. So see that the second force, a component F cos 30 is along negative y direction and the component F sin 30 is along positive x direction. So what you can do is, since this is along positive x direction, so we can represent it in vector form something like this, F sin 30 into a unit vector along positive x direction, which is I cap, and next thing, the y component is F cos 30 into a unit vector along that direction. A unit vector in the direction of negative y will be minus j cap. So it becomes minus F cos 30 j cap. So the resultant, the sum of these two forces is the total force acting on this mass m placed over here. So that resultant force is equal to sum of these two. See that minus F sin 30 and plus F sin 30 gets cancelled. So the resultant will be minus 2F cos 30 j cap. So this minus and j cap represents that the resultant force acting on this mass will be along the negative y direction, or in this situation along this angular bisector. So this is the other way of finding the resultant force acting on one of the masses. Okay, so you can copy this and I will erase this. Just pause it for a second and then you can copy this. And the next thing what we'll be doing is, so having explained this in detail, the next thing I will not be explaining in detail, because the next one involves the same procedure of finding the resultant force. The only difference is that instead of 3 masses, we'll be having 4 masses placed at the 4 corners of a square of side A. Okay, so instead of explaining in detail each and every step, I'll just give you a general idea of how to solve such a problem, where let's say we have 4 masses, and for the sake of simplicity, let's take those masses m placed at the 4 corners of the square. So at this instant of time, or let's say we have placed the 4 masses, we have fixed 4 masses at the 4 corners of a square of side A each. So okay, each side length is equal to A since it is a square. Now we want to find the we want to find the resultant gravitational force acting on one of these masses, any one of those masses, due to the other three. Okay, so let's say we want to find the gravitational force on this one due to the other three. Okay, and for the sake of simplicity, let's give some numbering: 1, 2, 3, 4. Okay, we want to find the gravitational force acting on 1, which will be equal to, or in vector form you can write something like this: force acting on 1 due to 2 plus force acting on due to 1 due to 3 plus force acting on 1 due to 4, from the principle of superposition. And the next thing what we'll do is, so instead of writing them in vector form, the simplest way is just to write their magnitudes and do them. And the magnitude F12 indicates the magnitude of this, the force, the magnitude of the force acting on 1 due to 2, which will be equal to G into product of the masses m into m square by the square of distance between them. Similarly, F13, the magnitude of this force acting on 1 due to 3, which is equal to G into the product of the masses, which is equal to, and again m square, but the distance in this situation is this length, or the length of the diagonal. In a square, the length of the diagonal is root 2 into a, root 2 into side. Root 2a whole square gives us 2a square. Root 2 into a whole square gives us 2a square. And the force acting on 1 due to 4, this one. Okay, force acting on 1 due to will be G into product of the masses, a square, by square of distance between them. Since these are the adjacent sides, adjacent corners of this square, the distance between them will also be equal to a. So this is the force acting on 1 due to 4. And having represented the magnitudes, I will just try to represent their directions. So F12 will act in this direction, F14 will act in this direction, and F13 will act in this direction, along this diagonal direction. Now how do you find the sum of these three? Okay, now what we can do is, and again the sake of simplicity, we can either go with the parallelogram law or go with the vector form I have used earlier. If we go with the parallelogram law, first look at F12 and F14. They're perpendicular to each other, and as well as they have equal magnitudes. Okay, they're perpendicular to each other and have equal magnitudes. So when they are perpendicular to each other, the resultant of these two forces will be F12 whole square plus F14 whole square. Remember that they have equal magnitudes. Okay, equal magnitudes. Or let me call, for the sake of simplicity, I will take G m square by a square is equal to F. If I call this as F, this is F by 2, and this is equal to F. Okay, because I don't want to write this entire thing in each and every step. So if I take this, then I can really write the I can write the the steps easily. So the resultant force due to these two is root of F square plus F square, root of 2F square, which is equal to root 2 into F. So root 2 into F is a resultant of these two forces, and see that since they have the equal magnitudes, these two have the equal magnitudes, the resultant of these two forces must make equal angle with each of them. Okay, since the angle between them is 90 degrees, the resultant of these two forces, they are something like this, F14 and F12. The resultant of these two must be in a direction where it makes an angle, equal angle with each one of them. Since this is 90 degrees, so if it has to make equal angle, it has to make 45 degrees with each of those forces. So the resultant must be making an angle 45 degrees with each of them, or it must be along the diagonal direction. So if it's along the diagonal direction, because you see diagonal makes an angle of 45 degree with each of these sides. So the resultant of these two forces must be along the diagonal direction, or it must be along the direction of F13. Okay, So since the resultant of these two and F13 are in the same direction, so the overall resultant is nothing but the resultant of these two plus F13. So the total force acting, I'm just writing the magnitude because okay, I'm not writing it in vector form. You can also do it in vector form by taking, I'll explain it last. F1, the total resultant force acting on the first mass will be equal to the sum of these two, because the resultant of those two is also along diagonal direction, and the third force is also along diagonal direction. You can add them directly. Root 2f plus F13. F13 is 1 by 2 of g m square by a square, or you can write it as f by 2. So the resultant force acting on one of the masses is f of root 2 plus 1 by 2, where f is g m square by a square. Okay, this is how to find the resultant of the resultant gravitational force acting on one of the masses due to the other three masses. And what about the direction? The resultant along this is along this diagonal direction. Okay, this is the way you can do it. The other way of doing this is, I'll just give you a basic idea of how to do this. The other way of doing this is, you can assume x and y coordinate system to be something like this. You can take x coordinate, y coordinate, something like this, then negative y and negative x. Then in such a situation, this force F14 is along positive x, F12 along negative y, and F13 is in this direction, and you can resolve it into two components, and you can add them, resolve it into components, and write the three forces in vector form, and then you can add them, you'll get the resultant. And even if you do it in that way, the magnitude of that resultant again comes out to be the same, f of root 2 plus 1 by 2, where f is g m square by a square. Okay. And the next thing I want to discuss is, see that whenever the force acts on a body, they definitely try to accelerate. Okay, they try to accelerate when a force acts on a body. This can be concluded from Newton's second law, first law. They all speak the same. So when a resultant force acts on a body, the bodies do accelerate, and the Newton's laws gives us a way to calculate that acceleration from the force acting on the bodies. Okay. Now we will discuss a simple one. Let's say we have two masses, m1 and m2, separated by a certain distance d. Okay, have two masses m1 and m2. So at this instant of time, when I'm looking at them, the separation between the masses is given as d. Okay, it's given as d. Now what I want to find is, in this situation, let's say I'm holding them, m1 and m2, I'm holding them at a separation of d by some means. Okay, or let's say at this instant of time they are in space, only these two masses are present, and they are not experiencing any force due to any other thing in the universe, they are present alone. Then at this instant, these two masses are separated by the distance d. We know that the force acting on each of them will be g m1 m2 by d square from the law of gravitation. So on each mass, this force acts. On m1, this force will act in this direction. So this m1 will experience force F in the right direction, and the same thing with m2 also. It also experiences the same magnitude of force F, but in the left direction or towards m1. Okay, they experience same direction, but they do have different masses. Okay, now how do we find the acceleration of each of the masses? See, for the force acting on this is F, and on this also F, but they have different masses. So the acceleration can be found from the Newton's second law, where in this situation, since mass is not changing, we can write force acting on this. There is only one force acting on this, so it is also the resultant force. Force is equal to mass of the first one into m1 into, let's assume its acceleration is a1 at this instant of time. Okay, if for the second mass the same force is acting, F, but it's in the opposite direction, I'm just considering the magnitudes here. So this mass m1 will have an acceleration a1 in this direction, and let's say the second mass m2 will have an acceleration in the left direction. Then in such case the same force is acting, then this will also be the resultant force acting on m2, which is equal to m2 into a2. Okay, m1 into a1, m2 into a2. See that since f both the same, m1 a1 must be equal to m2 a2. m1 a1 is equal to m2 a2, or we can write m1 by m2 is equal to a2 by a1, or we can say that when here if you observe that the mass or the accelerations are inversely proportional to their masses, or what it means is that the more, suppose if we have two bodies, one heavier than the other, okay, one heavier than the other, the one which is heavier will have less acceleration and the one which is lighter will have more acceleration. Okay, more acceleration. That's what we can consider from this. See that the accelerations are inversely proportional to the masses. So heavier the mass, lower the acceleration. See that the one important aspect of this is we see the earth is a very heavier object when compared with everyday objects we use, something like a car, an aeroplane. Aeroplane may be big when compared with our size, but when it's compared with the size of earth, it's very small. So that's why whenever aeroplane stops working in midair, okay, it is being pulled by the gravitational force of earth. If this is earth, if a plane is flying something like this, okay, and something like this, or let's forget about this, let me draw it differently. This is ground. If a plane is flying in air and wherever its engines start working and the earth pulls it downwards due to the gravitational force, and as a result see that this plane will also exert the same force on earth. If this plane is experiencing a force F in the downward direction, the earth will also experience same force due to this plane towards the plane. Okay, each of them will try to attract each other. But the main important thing is that we don't see much movement in the earth because its mass is very higher when compared with the mass of the plane or helicopter, whatever it is. So because of the mass of helicopter being very low, it comes to the earth, it hits the earth with a very high acceleration, or it will have a lot acceleration. But when you compare the acceleration of earth, when you see the acceleration of the earth, it's going to be a lot smaller because of its heavier mass. So we can conclude this from this. So when you have two masses separated by certain distance, okay, when you release them, they try to go towards each other and they try to attract each other with the same force, but they will have different accelerations depending on their masses. Okay, and if they have different masses, the one with higher mass will have less acceleration and the one with the lower mass will have the one with lower mass will have higher acceleration and the one with higher mass will have lower acceleration. Okay, that's it for now. In the upcoming video I will try to explain a few more examples related to this. Okay, so I hope you understood everything, and if you understood everything, please share it with your friends, which can be helpful for them, and also try to leave a comment, okay, if you have understood well. And for more learning, subscribe to my channel, and have a great day.